at NS, one of the classes is very annoying because you have a central board and two small screens on each side, and then that means that half of the room is watching one screen and you're pointing on the other screen, and it's very bad. At least here it's central. Yeah. Yeah. So those are former postdocs, former PhD students. Aife is my current PhD student. Patrice, you know. Olivier is the newcomer. Watanabe and Taniguchi are growing the BN crystal to encapsulate the crystal. Yeah, in Japan. Rebecca is my wife, and she works at C2N doing graphene things, and we work together. Yongjin, you might have maybe not met, but he works a lot with, he basically does fabricates the sample for Gwendal, and he also produces him with a former student of his, Chuan, the amplifiers that we use for noise measurement. And then other people from Spec, Carles, and guys like this. Ben. I haven't listed the new guys at TNS, Gwendal and Gerbo, and yeah, and with Erwan as well, with you too, with you know, the list of collaborators becomes longer and longer, and it's quite nice. It's yeah, it's yeah. I think mine. yeah, that's. I think. I mean, it's already bad when you're in the audience and your phone rings, but when you're giving the talk,
you are allowed to do everything. I
mean, with some limits. I think it's fine. Yes, I have no alarms, no nothing. I'm good. It's a little bit of a strain on the neck, but je pense que c'est le plancher noir de la salle qui fait un truc. Ce serait en faux bois ou autre chose comme ça. Ce serait un peu moins. Ouais, ça. I'm here all day, so at some point the food is going to arrive, so we should stop. c'est mieux. Enfin, je vais leur dire qu'ils peuvent, s'ils veulent poser des questions tout de suite, ça me va. Si j'arrive pas à la fin du talk, c'est pas très grave. Hi, it's me. Yes, I'm delocalized between Saclay and Paris. Yeah. All right, thank you. Can you guys hear me? Yes, cool. So thank you very much, Dario, and thank you for the invitation. Hi, everyone. I'm really, really happy to be here. My first time in Genoa, and first time here at the university, and I'm really enjoying all I'm seeing here. So indeed, I'm working on graphene and heat transporting graphene, and I'm going to try to give you a rather broad and, let's say, not too technical overview of what we do, why we do it, and what are the challenges. Before I start, if maybe I will go here because I can see the screen better and I can see you guys better as well. If you have any questions, if you want to ask a question during the talk, feel free to do so. I'd be happy to answer it. If you don't get to the end of my talk, it's fine because I will have explained you a lot of things. And after that, we have some food, so I know that I shouldn't say too long. And I wanted to say. So as you said, I've been in CA-Saclay with this for the past 10 years and being which is smack dab in the Paris, a bit much nicer, less lab space, but you know, that's how it goes. So I'm going to give you an overview of my activity as mesoscopic heat transport. It's of course not my, my sole work. It's a very collaborative process, and everything I'm going to show you is mainly the work of those 4 persons here: Raphaël Delagrange, Manjari Garg, who are postdocs from 2019 to 2024, and Gaël Le Breton and Aifei Zhang, PhD student. Aifei is currently finishing her PhD. And I'm working very closely with my colleague in Saclay, Patrice Roche, Olivier Maillet, as well as the obvious collaborators whenever you do graphene, Kenjin Watanabe and Takashi Taniguchi, NIMS in Japan, who grow hexagonal-boron nitride crystals that we use in our graphene devices. And we have a close collaboration with people at C2N, Rebecca Ribeiro-Palau, Yongjin and Chuan Dong on the experiments. And we have also very fruitful collaborations with theorists and other experimentalists, and of course, with Dario and Mara here. Okay, so I'm basically in our group, we're mesoscopic physicists, which means that very broadly speaking, we study electronic systems made in maybe new materials, maybe in standard materials, but whose size might be large compared to the atomic scale, but still they are quantum. So essentially what this means is that we're going to study electronic circuits which might host a very large number of particles, a large number of electrons, but still the number of degrees of freedom is quite small. Okay, and basically when you play with those kind of objects, then you can always somehow reduce your system into something quite basic that will be represented by this. Those are reservoirs which contain a large number of particles which are in thermodynamic equilibrium. So you can define a temperature, some entropy, chemical potential, a number of particles which is macroscopic. And in between those 2 reservoirs, you have a small conductor which has reduced dimension. And of course, it can be 0D, it can be 1D, it can be 2D, but usually it's something small, such that the wave function inside this conductor becomes quantized, essentially exactly as would be sound wave inside a tube. right? So essentially what this says is that any quantum conductor is some kind of waveguide for quantum particles, and those can be electrons, but those could be photons or whatever you like. This means that in a single particle theory, you can describe this kind of stuff as a set of independent transport channel, as essentially decomposing transport into these different modes. So for instance, here I'm showing a fundamental mode where you have most of your, let's say, wave function that is centered inside this channel, and then the second mode, which is split in two, and so on and so forth. And essentially, this notion of quantized transport means that the simplest quantum conductor that you can have is a conductor that only has one quantum channel. So again, I have my two reservoirs here, and then I'm connecting them through a channel that has only one mode. And then if you do so, essentially you can very easily calculate that the transport properties of this channel becomes quantized, because you only have one channel, and you only have any given charge, a number of charge that you can carry per unit time, or any given unit of energy, and I'm going to talk about that. And so essentially what this tells you is that you will have the apparition of quantized electronic conductance. So essentially the conductance of a single electronic channel cannot exceed the quantum of electrical conductance E square over H. And this was already seen in the quantum Hall effect experiments, which I'm going to mention. So this is about 30 to 40 years old. And the fun stuff about this is that it's completely universal in the sense that you can obtain the same value regardless of the material as long as it's ballistic and it contains electrons, right? And this is something very, very, I mean, this quantity is really 1 over 26 kiloohm. It's really the linchpin of electronic quantum transport. Any mesoscopic quantum experiment will conductance that you with this quantum of electrical conductance. So the more fun, well, this is very fun. The even more fun quantity that I like to play with is heat transport. And the idea is that you don't have just quantization of charge transport in a 1D system, you also have quantization of heat transport, and I'm going to give you some insight of why this is so. And essentially, you can, again, quite easily, using, for instance, scattering matrix formalism, calculate that the heat flow that is carried in this one-dimensional channel connecting two reservoirs at a temperature T left and T right cannot exceed this value, which is the quantum limit of heat flow, pi square kb square over 6h times the difference of the square temperatures. And the really interesting stuff about that guy is that it's even more universal in the sense that not only doesn't it depend on the material, it also doesn't depend on the quantum statistics, on actually the nature of this object that are carrying the energy. It's the same for electrons, for photons, for phonons, even for those anionic particles that emerge in the fractional quantum Hall effect. And this is actually a rather small, so it's a power, right? And essentially those are small powers. It's half a picowatt per Kelvin square times the difference of the temperature square. It's in the femtowatt range. Okay, so how can we understand this thing? And in the following, I'm going to write this prefactor pi square kb square over 6h as kappa naught over 2. And essentially, you can either do the full calculations, right? Or you can try to intuit that. And for instance, for electrons, you can use Pauli principle to get an intuition of why they have this shape of kT square. And essentially, the idea is to consider a 1D system that carries electrons. Those electrons have wave function. The width, the temporal width of this wave function is typically h over the available energy scale that you have, which is kT. And so you have small blobs of electrons that have a width h over kT that are spaced also by h over kT. And because of Pauli principle, you cannot have two electrons in the same state at the same time. So they are well ordered one after another, such that when you compute the heat flow, the amount of energy per unit time is essentially the amount of energy is kT. The unit time is h over kT. So the heat flow is kT squared divided by h. So this is, again, just a hand-waving argument. In order to get the pi square and the 6 and all the stuff, you have to do the full calculations. But this already gives you an idea why this heat flow is proportional to the temperature square. And actually, if you want to do that with photons, it's even more straightforward. You just use Planck's law in 1D for a single mode. Okay, so today, this talk, I'm going to show you how we measure this quantum limited heat flow in an electronic system, mainly in the quantum Hall effect regime. And also, I'm going to show you examples of the kind of experiment we can do with that once you're able to measure this quantity and evaluate this quantity with respect to other heat flows. Okay, so you want to measure an electronic flow, which might seem cheaper, but it's actually quite complicated. Because, you know, measuring a charge flow, measuring a current is rather easy. You need a meter, you need an ammeter, you need some apparatus, a multimeter, that exists commercially. Here, what you want to measure is essentially, you want to measure the power transmitted between two reservoirs that have different temperature. So essentially, you need to engineer first this one-dimensional electronic channel and make sure that it's ballistic, right? Then you need to engineer electronic reservoirs, so reservoirs of particles that have well thermalized and in which you can define a temperature, and you need to tune and measure the temperature independently. And finally, you need some kind of power meter that allows you to measure this heat flow, right? And so essentially what this means is that you need to have a one-dimensional ballistic electronic channels that is quantum coherent. So that means that experimentally, you'll need cryogenics, you'll need nanofabrication to realize the systems. You need some kind of thermometry to get access to this temperature, and some more subtle kind of power meter. So in practice, what we like to use for our experiment is 2D system in the quantum Hall effect regime. And essentially, the idea is that, so are you guys familiar with the quantum Hall effect? Have you at least have lectures on that? It seems so, maybe not, but I'm going to give you a very, you know, let's say, broad approach to what it is. So essentially, the idea is that you take a two-dimensional electronic system, and I'm going to give you an example of actual physical system that can host a two-dimensional of electron, and you apply a strong magnetic field proportional to it, perpendicular to it. And so the idea is that at low temperature, high enough magnetic field, what you obtain is that the center, the bulk of your 2D system becomes insulating, and all the electronic current is carried along the edges of this two-dimensional electron gas. And essentially, you can understand that semi-classically. The bulk are essentially trapped into cyclotron orbits that do not move, so they do not take part into transport. This guy is never going to find a way to diffuse from here, this metallic contact, to here, whereas the electrons on the edges still do cyclotron orbits, but they bounce basically on the edges and can propagate. And quantum mechanically, essentially this quantum Hall effect arises because at large enough magnetic field, your electronic spectrum, which is normally something continuous, it's a Fermi function for a metal, becomes quantized into what we call Landau levels. So essentially, whenever you put your Fermi level in between two Landau levels, you have something that is an insulator at bulk, and you have conductive edges. And the very nice and very important stuff, as far as we were concerned, is that the electrons along the edges are carried by a quantized number of edge state, which are one-dimensional quantum channel. They're 1D because they follow the edges of the sample. They're chiral because the direction is only set essentially by the product of the direction of the magnetic field and the sign of the charge. If it's electron, it goes in one direction. If it holds, it goes into the other direction. And that's pretty much it. And the very important stuff as far as heat transport is concerned is that those 1D chiral channels are dissipationless, in the sense that there is no voltage drop along this, there is no dissipation, no voltage drop along this path. Essentially, if you put an electron here, it has 100% chance to arrive on the other side. Right. And so this appears quite clearly when you measure the electrical conductance, so the inverse of the resistance of such a sample as a function of the density, essentially as a function of the position of this Fermi level, where you will see plateaus that are extremely well defined in units of E square over h. That corresponds to the quantum Hall effect. So essentially, when you have a 2D system and you're sitting on this kind of plateau where the conductance is quantized to 2 E square over h, you can be sure that the bulk is insulating and all this transport goes through those 1D chiral dissipation at edges. So those are our 1D electronic channels that are ballistic, and this is where we do our heat transport experiments. Okay, so before I show you the experiment, I mentioned the different materials. Essentially, you need any kind of material which might host a 2D system, a 2D electronic system. And so, for instance, the most let's say, the historical candidate and the most widespread one are heterostructures of gallium arsenide. So essentially, a heterojunction between gallium arsenide and gallium arsenide doped with aluminum. At this junction, at low enough temperature, you essentially, so it's something that is grown with molecular beam epitaxy. So this junction is really atomically perfect. And here at this junction, at low enough temperature, below 100 Kelvin, you have a two-dimensional plane of electrons that are really free electrons that are completely detached from the crystalline lattice, and that can have very, very high mobilities. The other well-known candidate, which is sort of my favorite, at least the one I'm working with on a daily basis, is graphene, which is this two-dimensional crystal of carbon atoms that are arranged in this honeycomb lattice. And again, this is very obvious. You have a two-dimensional crystal that is a metal, thus the electrons on there live in 2D. All right. And of course, you have quite a lot of different materials, bulk semiconductors, but also other 2D materials that you can exfoliate. And right now, there's a very large excitement on transition metal dichalcogenide, on twisted bilayers or either graphene, TMDs, and all this kind of stuff. But I'm not going to go into too much detail here. Okay, so before I move on to the experiment, let me give you a very broad overview of the kind of stuff that you can do in mesoscopic physics with those one-dimensional edge channels. And one very obvious comparison, or at least an analogy that you can make between electronic transport is in those 1D edge channels on the quantum Hall effect, that with the transport of photons into a fiber optics. Essentially, with those edge channels, what you do is define a channel, some kind of rails, on which the electrons propagate and then propagate until they reach the end of the sample. And that's very much what you have in a fiber optics. And so the idea is that you can try to realize the electronic equivalent of a lot of different optics and quantum optics experiments. And for instance, you can do electron interferometry. For instance, you can define a Fabry-Perot, where here you have a graphene sample with these closed cavities using gates, in which the edge channel essentially loop inside this edge channel. And so the electrons in this loop interfere with themselves, and this gives rise to interference. It's exactly the electronic analog as the Fabry-Perot interferometer. You can have the same kind of stuff with Martzender interferometer, where you need to define beam splitters for electrons. And essentially, you have a beam of electrons that you split in two paths, one here and the other there. You recombine it on a second beam splitter, and you have interferences, again, like in optics. You can also do collisions experiments, and essentially here what you will do is not only use these properties of the edge channels that are like fiber optics, but also use the fact that electrons quantum mechanically are a wave, but they are still particles, and so you can try to collide two grains of particle one with another. This, for instance, you can do Fermi-Hong-Mandel experiments where electron sources to electrons to collide on a beam splitter and see how fermionic statistics and Pauli principle will affect the outcome. And you can use this kind of geometry to essentially put into light those fancy new quantum statistics, those anionic statistics that you have in a fractional quantum Hall effect. And this is also something that is done by my colleagues now at ENS. You can look at more subtle stuff, like exactly, because right now I've pretty much told you that you can take any kind of system and essentially map it onto a set of completely independent transport channel. And I'm, for instance, assuming here that the different edge channels that circulate around the sample are independent, but it turns out that they're not. They can exchange energy. And this is something that you can probe, and that's a work that we've done with Dario and Maura. And finally, what you can do, and what I'm going to talk about today, is ballistic heat transport. And as a baseline, all those experiments to be at magnetic field, typically at 10 Tesla, and at very low temperature, 10 millikelvin, so 0.1 degree Kelvin, 0.01 degree Kelvin above absolute zero. Okay, so yeah, I'm going to talk about this today. Right, so how exactly do we measure heat transport in the quantum Hall regime? Again, so we have this 1D system, it's those 1D edge channels. That's already one requirement of the experiment done. But now we need to have a thermometer. We need to define a sources for hot particles and a source for cold particles, and we need to measure the power that is exchanged. And so in order to do that, we use this geometry. So this geometry, this cartoon shows a piece of two-dimensional electron gas. of the talk, it's going to be easier. So you have a piece of graphene that is split into two parts, one here and one there. And those two parts are connected by this red brick. And what this red brick is actually a piece of metal that is actually quite small that connects electrically those two guys. And the important stuff is that this piece of metal, this metallic contact, is called floating in the sense that it is only connected to the flake of graphene, and it's not connected to wires of the experiment or something else, or compounds, or whatever you want. On the other hand, you have those smaller bricks here that are also electrodes, but those electrodes are, contrary to what you see here, actually quite large, and they are connected to the wires of the experiment. So for instance, you can connect them to DC current feed, you can connect them to some cold ground that I haven't shown you here, and you can connect them to some apparatus that allows you to measure the temperature. And the idea behind this, this geometry is that this central floating contact is going to be the source of hot electrons, whereas the larger blue contact here is going to be the source of cold electrons, and what we're going to do is to probe the heat exchange between this guy and all those guys, all right? And so the idea is that you take this sample, actually fabricate it, you put it into a high magnetic field such that you reach the quantum Hall effect regime. So all the electrons now go on edge channels around the edge of the sample. And the bulk is, of course, again, insulating. And so the idea is that if you flow a DC current, if you impose a DC current here, it's going to flow down this edge channel, reach this central contact, and essentially here what you have is the equivalent of Kirchhoff's law, where this central contact is just a node that split the electric current equally between this branch and that branch, okay? And so essentially what you have here is a splitting of current, and essentially you have a voltage drop here that is accompanied by power, by joule power dissipated inside this contact. And you can quite easily calculate that the joule power dissipated into this contact is written by this. It's 1/4 of the, essentially what is the resistance of the sample, so 1/4. Nu is called the filling factor. It's essentially the number of electronic channels that are flowing around your sample. And it's tuned by both the magnetic field and the density in your system. And essentially, this, all of this times I squared. So this is a joule power, right? It's a resistance times a current squared. And the idea is that you dissipate some joule power into this small island of electron, which means that the temperature of the electrons in the island is going to rise, all right? And this increase of the electronic temperature in this island that I'm writing Tc will be essentially given by a rather simple heat balance, which tells you that in the stationary regime, where you're still basically flowing DC current into your sample, it's being split at the island, you dissipate joule power. Then the joule power that you dissipate into the island, 1/4 of Ri squared, is equal to the total heat flow carried by all the edge channels that leave the island. And the number of edge channels that leave the island is equal to 2 because you have two parts of the sample. So you have two branches, one here and one there. You have n, the number of edge channels on each edge, times kappa naught over 2, Tc squared minus C naught squared. This is, as I was telling you before, this universal quantum limited heat flow for a single channel. So you have a heat balance that's quite simple. You know, again, joule power dissipated here, the temperature increases, and the increase of temperature is set by the amount of heat that is allowed to leave the island at a given time. All right. And so the idea is essentially, now you have this heat balance and you want to probe it experimentally. And what you do is that this quantity, the resistance of the sample, you just measure it with a fancy multimeter. That's easy to do, easy-ish, right? You know the amount of current that you apply to the sample because you know which button on your current source you've pushed. And then you need to essentially evaluate this term, this right-hand side of this equation. And essentially the idea is that if you find a way to measure those two temperatures, Tc and T naught, and T naught is really, it's called the base electronic temperature, then you can infer this quantity. And the way to essentially measure this is to measure the current fluctuations in the sample, the thermal noise of the sample. And essentially you can view that as, thermal noise is something that's not particularly quantum. Essentially when you resist at a finite temperature, the thermal agitation of the electrons inside of your resistor is going to give you rise to fluctuations of the current inside of this resistor. And those fluctuations are directly proportional to the temperature. And essentially, we use this proportionality we measure the current fluctuation, and we infer this. Okay, so then it's simple. This you know, this and this you know, then you can infer this quantity. Okay, so before I show you the experiment, let me mention that, first of all, you need to fabricate the samples. So either you use gallium arsenide, and then you have friends who grow samples. You go into the clean room. You do whatever you need to do to obtain a sample. In our case, graphene. And essentially, if you want to do quote-unquote interesting experiment in mesoscopic graphene, then you need very, very clean samples. And the way to get very clean samples is essentially to use graphene, right? You just take a pencil, you scratch it, everyone knows about that. But you need to actually protect graphene from any contaminants, from water, from air, from polymer that you use in the clean room. And so the idea is that you're going to encapsulate it between two slabs of a 2D material called hexagonal boron nitride, or BN, or HBN, with the idea that this material, HBN, has more or less the same crystalline structure as graphene. It has the same Olicom lattice with pretty much the same lattice constant, but now instead of carbon atoms, it's made of boron and nitrogen. And this is a very good insulator. This is a very good dielectric. It's atomically flat, so whenever graphene sits on boron nitride, it's very flat. It has no wrinkles, nothing that could scatter the electrons. And this is how, when basically you make a sandwich out of that, and that's a typical microscope image of this kind of sandwich that we can make in our lab, where you have here the flake of graphene that you have to highlight because it's really hard to see with the microscope. That is sandwiched between a top BN and a bottom BN. And just for numbers, the thickness of those BN layers are in the tens of nanometers, between 10 to 40 nanometers typically. So those are not, single atom thick. All right, so basically whenever you do that, you contact them, again, you go and work in the clean room, then you get something that sort of looks like this. This is an optical image of one of the devices that we worked with in the recent year. It's getting quite old, that guy. So essentially here in green, this bar is where the graphene is. Those yellow/gold things are the metallic contacts that are deposited in order to create an electrical contact to graphene. And in particular, this central rectangle here is exactly this floating central ohmic contact that we're going to use as a source of hot electrons. And here you can see the other electrodes that are symbolized by those guys that are actually way larger and that extend way, way beyond the field of that image and connect the leads of your experiment, and for instance, to cold grounds, to gate voltage supplies, to noise amplifiers, to measurements, and so on and so forth. And I was mentioning that you can get the temperature in the sample using noise measurement, and indeed, there's again, it's Johnson-Nyquist noise. It's the thermal agitation of the electrons inside this sample that is reflected into the fluctuations. And essentially, by measuring noise that we call delta S, we can, through this formula, directly obtain the increase in electron temperature in the island, right? So you just need to measure that guy, apply this formula, and you get the temperature. Okay. Right? Maybe just to be thorough, you might have noticed here that I've mentioned that there is a plane of graphite below the sample. This, essentially, we use as an electrostatic gate to tune the carrier density, to tune the Fermi level in the system. And we like to use graphite because it comes from the same exfoliation process as graphene, this famous Scotch tape technique. And the idea is that this is a rather bad metal, but you don't really care. You just apply a voltage on that. Flat. So all of this structure is super, 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 super flat, and due to have very high quality sample where you can see nice quantumal states, fractional quantumal states, and so on and so forth. Okay, so yeah, a little bit more on experimental conditions. I was telling you that generally the experiments that you do for quantumal mesoscopics need to be done at high magnetic field, so 10 Tesla, and low temperature, so below 0.1 Kelvin. And for heat transport, actually you need to go a little bit further than that. And mostly you want to really stay in ultra low temperature regimes. And mostly the idea, and this is a little bit technical, is the fact that if you're at too high temperatures, then the electrons, the hot electrons inside of those small metallic islands start to become coupled to the phonons, to the vibration of the metal. and they start to lose energy and lose heat into the phonons of the metal, and that adds another term to this heat balance that controls the increase of temperature. And this is interesting in itself, but you'd rather like to avoid it, at least if you just want to probe heat transport by the edge channels. You have to stay in electron temperatures on the scale of 10 millikelvin up to maybe 100 millikelvin, not more than that. And this is really, really hard to do. And of course, do noise measurement to measure this thermal noise in order to get the temperature. And actually, you need to have, because you work at very low temperature, you need to have very high sensitivity to be able to resolve an increase in the electron temperature inside of this island of about 1 millikelvin. And this means that you have to work quite well to obtain a high sensitivity noise or current fluctuations measurement setup. But once you do that, you stick it into this kind of dilution fridge. You ask students to close the fridge, and you give them a hand because it's fun. And then you do the experiment. And so the experiment, after characterizing the sample, making sure that it works, typically gives you something that looks like that. This is the increase in the electronic temperature in this central island, in this hot electron reservoir, as a function of the DC current that you flow into the sample that you use to heat up the sample and this ohmic contact. And as you can see, and we've done that for 3 different filling factors in this image. And again, the filling factor is supposed to count the number of channels, this 1D ballistic channels that flow around the sample. And essentially, that's the kind of data we have for nu equal 1. So we expect 1 channel, 2 channel, 3 channels, and you get those V-shaped curves. And essentially what this tells you is that this V-shaped curve tells you that at high enough heating current, the temperature becomes proportional to the current. And it's actually quite nice because that's what you expect from this formula, where at high enough Tc, at least when you can start to neglect T0, then you have I square proportional to T square. This gives you this slope. So essentially, the slope in here should be given by these 2 n kappa naught over 2, blah, 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 all those kind of stuff. And what you can see as well is that, so I've shifted the curves just for clarity. They should all start from this point. But essentially, what you can see is that the lower the filling factor, so the lower the number of edge channels circulating around the sample and cooling down the island, then the higher the temperature for a given heating current, right? This guy increases way faster than that guy, which means that essentially in this filling factor at nu equal 1, you have a less thermal flow cooling down the island. Okay? So essentially what we do now is to make sense of this data, which are pretty much the raw data that you get from the experiment, in terms of that heat balance. So what you'll do is essentially use this kind of plot where on the y-axis you plot the heat flow that essentially you calculate from the DC current. Again, you know that guy and you've measured that. So you have the heat flow in some unit of half kappa naught because it's going to be convenient. So it's in Kelvin square. And you plot it as a function of the difference of the 2 temperatures that you've obtained using noise measurements, right? And if you do so, then you would expect your data to fall onto straight lines because again, the joule power here is proportional to Tc square minus T0 square, where essentially in these units, the slope of those lines is integer, is unquantized. Okay? So essentially at nu equal 1, for 1 channel, you would expect to have something like this, 2 channels, something like this, 3 channels, a slope of 3. And indeed, if you put the data at nu equal 1, it falls on one channel carrying heat, and 2 and 3, respectively, 2 and 3 channels carrying heat. So, yay, it works. It's one fun, so that's the direct way to show that heat transport is quantized in the quantum horrific regime. Maybe one little side note is that people usually speak about quantized thermal conductance. It is indeed quantized, but you see that the heat flow, so the heat current, is in T square. And the conductance is the first derivative of the current with respect to the temperature. So the conductance will be proportional to T. So you have a conductance that is quantized but proportional to T. It's a little bit messy. I'd rather just play with this data and show you how the slope is quantized, right? And what this tells you is also that in this integer quantum effect where you have essentially fermionic system, fermionic channels that carry charge and carry energy, then the Widman-Franz law that links the thermal conductivity to the electrical conductivity, a classical metal, is basically respected. And essentially what the Widman-Franz law gives you is that the thermal conductance is proportional to the electrical conductance, and the proportionality constant is the Lorentz number times the temperature, so pi squared Kb squared, that we know from this kappa naught formula, divided by 3e squared times the temperature. So this works for fermions, essentially because you can view in first approximation the electrons on edge channels of the integer quantum effect as free fermions, or at least weakly interacting. Okay, another really fun stuff. So maybe just as a disclaimer, this is data from our lab. It's not the first time that people measured quantized heat flow. It was done in the first time in gallium arsenide in 2013 in the group of Frédéric Pierre, who's now at C2N. I used to be a postdoc at that time. And it's been done also in graphene in 2019 in the group of Anindya Das in IIT Bangalore in India. Okay, so another quite interesting stuff is that you can do the same experiment if your sample is clean enough in fractional quantum effect, where essentially, I'm not going to give you much detail about the fractional quantum effect, but essentially it's a quantum effect where interactions become completely dominant and where the particles, the excitations of your system are not fermions anymore, they're anyons that have a quantum statistics in between bosons and fermions. And this gives you rise to essentially excitations that have a fractional charge, typically 1/3 of the electronic charge, that have weird quantum statistics that can't really be probed with heat transport up to some special cases, but that behave for intent of purposes like the integer quantum effect. You have edge channel that flow around your system and a bulk, and an insulating bulk. And essentially here, those hexagons represent the data at nu equal 1/3, which is the prototypical fractional quantum Hall state. And as you can see, 1/3 has the same thermal conductance of the same thermal flow as nu equal 1. And that's quite astonishing because the electrical conductance of nu equal 1/3 is not at all that of nu equal 1. It's 1/3 of that of nu equal 1. So you have a system that conducts way less electricity, but the same amount of heat, right? And 1/3 typically violates the Widman-Franz law because you don't have, I mean, it's still proportional, but the proportionality constant now is 3 times larger, right? And so generally what this tells you is that as soon as you have a mesoscopic system where you have strong electronic interactions, then this Widman-Franz law breaks down. That's a quite general statement. And again, this heat flow for anyons was first measured in the Weizmann Institute in 2017 and done in graphene in 2019, and we were able to do that a couple of years ago as well. Okay, how much time do I have? Ah, perfect. Right, so, okay, now you have a system where you're able to measure a quantized heat flow. You're able to show that whenever you have a one-dimensional ballistic channel of whatever particles you have, be they fermions or anyons, the electrical conductance is quantized, the thermal conductance is quantized as well. You can measure that thermal conductance. So what can you do with that? So typically, what we like to do, and which is a little bit more convoluted, is to try to look at the deviations to this quantization. And the idea is that we're still going to use this kind of geometry, but now we're going to connect this reservoir of hot electrons, this floating contact, to some region of the sample that has weird properties, most of the time where electronic interactions are very important, and where you expect to have modes, collective modes, like, for instance, spin waves or something else, dipoles that do not carry charge but carry energy. And the idea is that whenever you do that, essentially this adds another term to this heat balance, and this allows you to characterize and detect some modes that you would not detect by a simple electron transport measurement, because those are things that do not carry charge, right? And we've done that with two quite symbolic states of, well, at least not states, but features of the quantum effect. The first one that I don't have time to talk about are neutral edge mode in the fractional quantum effect, which are essentially also modes that propagate around your sample, but that go in the other direction with respect to charge transport, and that do not carry a charge, but only carry energy. And this you can detect this kind of heat transport experiment, and we've done that in And the other that I'm going to skip kind of rapidly because it's getting late, a rather weird insulating state that appears in graphene that is called nu equals 0. And the idea being that since this state is insulating, I mean, you can try to do electronic transport measurement in this. It's going to tell you that it's insulating, and that's pretty much it for that. So if you need to have more information about this, well, doing heat transport experiment might be a good idea. Okay, so in the last few minutes, I'm going to give you a very brief overview on that guy. I won't go into all the details because it's already the end of the talk, and I think most of you guys are getting hungry. But this plot here is a measurement. It's a typical measurement of the electrical conductance of a flake of graphene that you put at low temperature, typically 20 millikelvin, immerse it into a strong magnetic field, and you measure really the electrical conductance as you would do with a multimeter as a function of the magnetic field that you apply perpendicularly to the sample, and the gate voltage, essentially this knob that allows you to tune the carrier density to change the position of the Fermi level. And so if you do so, you have those kind of maps that are called Landau-Fan diagram in the community, where you have those very large domains at finite magnetic field where basically it's domains where the color is constant. The color is constant means the conductance is constant. It's not just constant, it's exactly quantized in units of square over h. It's exactly the data that I was showing you before, where you see those plateaus. So those things are the plateaus where you have the quantum Hall effect, where your sample becomes insulating in the bulk and have all the conduction around the edges. And you can see that by changing either the magnetic field or the gate voltage, you can change from all of the states. Essentially, you can go on this staircase. And for instance, if you reduce at finite magnetic field, if you reduce the density, you can change the quantum Hall state and the number of channels carried along the edges from nu equals 6, nu equals 5, nu equals 4, 3, 2, 1, down to this region. It's kind of hard to see maybe the difference between nu equals 1 and this region. This has finite electrical conductance, exactly square over h. And here in this region, your electrical conductance drops. Your sample becomes insulating. And that's something quite rare because graphene is not an insulator. It's not supposed to become insulating at a high magnetic field. And this corresponds to a quantum Hall state where both the bulk and the edges become insulating. So you have completely gotten rid of those edge channels. And it's a decent insulator. If you measure the resistance of that guy, it shoots up to above megaohm values at low temperature, and then it becomes hard to measure. And it persists. I mean, it's up to quite high temperature. You can see that up to 5 Kelvin or so. And you can see that from rather smallish magnetic field above 1 Tesla. Okay, and it's essentially something that you see in pretty much every device that you make. It's clean enough, and it has bugged the graphene quantum Hall effect community for the past 20 years. And essentially, we're not exactly sure why and where it comes from. And the idea, and that's where I'm going to get a little bit more technical, and please again interrupt me if you want me to clarify things. But the idea is that if you look at the spectrum of levels in graphene, again, how the electronic spectrum condenses into quantized level, in graphene it's going to look like this. Are not evenly spaced. You have some lambda levels for the conduction band, lambda levels for the valence band. Close to the edge, those lambda levels bend either upwards for electrons, downwards for holes. This is where you will have those edge channels. And here, what you can see is that exactly at zero energy, where you have this so-called direct point, where the valence and conduction band of graphene touch one another, then you have a lambda level. And this lambda level is kind of particular because it's made half of electrons, half of holes, and it has several symmetries. It has a spin symmetries, so spin in this lambda level can be either spin up or spin down, and it has what we call a valley degeneracy. Essentially, you have two non-equivalent points in your Brillouin zone where the electrons can live, either what is called K or K prime. And the idea is that if you allow interactions to become strong enough, then you can get essentially a spontaneously spin up and spin down will not have the same energy. Valley K and Valley K prime will not have the same energy. So essentially, you have something that is fourfold degenerate here that splits into 4 branches, right? And essentially, a whole game of understanding nu equals 0. So nu equals 0 is going to live here, where you have all of a sudden something that is completely gapped. You have a gapped bulk, but also gapped edges, right? If you raise your Fermi energy, now at some point, your Fermi energy will cross those sub-Landau levels, and you get, again, a gapped bulk, but you have now conducting edges. You have the usual Quotable effect, all right? So now the idea is to understand exactly what breaks the symmetries and how it breaks it. And as far as we're concerned, to try to understand how we can understand, well, basically how we can probe this guy and how we can probe this physics using heat transport. And very broadly speaking, you have a lot of questions that are related to that. Essentially, you want to know whether this splitting of this fourfold degenerate Landau level into 4 sub-Landau levels that are completely spin and valley polarized, is it either spontaneous, is it due to electron interactions only, or is it due to external factors such as the Zeeman effect, because you have spins in a large magnetic field? Yeah, maybe Zeeman effect plays a role, or something else. And essentially, you want to see whether this splitting of valleys or spin is larger than the other, which is going to change your phase diagram. And essentially, it boils down to what is the ground state of this weird insulating nu equals 0 state, and what are the spin and valley polarization. And of course, what kind of experiment can you do with this? And here I'm putting a list that is not complete of all paper, well, not all of many theory papers that have tried to tackle this issue, and you can see that it dates as far back as pretty much the beginning of graphene, 2006 in that case. Okay, let me very briefly walk through the different ground states that you can expect for this insulating state of graphene. And for this, I'm going to use something that is actually not an approximation, that is an exact result, and that is very convenient. And that is that in this Landau level that sits at 0 energy where you have nu equals 0, you have a direct equivalence between this weird valley degree of freedom that lives in Brillouin, in Fourier space, on the Brillouin zone, which I'm always struggling to put some sense on that. And essentially, this valley degree of freedom becomes completely equivalent to the sublattice. So we can forget about K and K prime. Now, everything we have to look at is on which of those 2 carbon atoms of the unit cell of graphene are the electrons living. And essentially, if you do that, then you can represent 4 main ground states for nu equals 0, the 4 main candidates, as actually putting 2 spins, one blue and one red, on the 2 sublattices of your graphene unit cell, right? And essentially, if you take into account the Pauli principle, the fact that you cannot have 2 spins that align in the same direction living on the same sublattice, then it restricts the number of candidates that you have. And so you can have, for instance, a ferromagnetic phase where the 2 spins have the same direction and each lives on their own sublattice, so red on A, blue on B, or yeah, let's say I put A in blue, whatever. Or something that is an anti-ferromagnet, where the red spin is up, the blue spin is down, and each lives on their own sublattice. You can have stuff that are more linked to sublattice texture. So for instance, this fully sublattice polarized phase that we sometimes call charge density wave, where the 2 spins are up and down, but they live on the same sublattice, and the other sublattice is left empty. Or something a little bit more subtle that is called the Kekulé distortion, where again the 2 spins are up, down. They share the same sublattice polarization, but now this polarization is a mix of sublattice A and B. Okay, so those are the 4 different states. What are the properties? And essentially, the idea is that all of those states have an insulating bulk. This ferromagnetic state has conducting edges, so you can already, if you see something that's insulating, it's not that guy. And actually, to reach this guy, this guy is basically due to Zeeman energy becoming larger than interactions. So you have to apply a very large in-plane magnetic field or screened interactions, and this is done in those 2 papers to obtain that guy. This is the usual candidate that everybody was thinking would be the main candidate for nu equals 0, but this was never fully proved. This you can obtain, this fully sublattice polarized, you can obtain in graphene if you align graphene with boron nitride, with the idea being that now you have 1 carbon atom that sits on top of a boron, the other on top of nitrogen, and which basically breaks this sublattice symmetry, and this basically forces the electrons to live on rather one sublattice than the other. And this calculate distortion, which was maybe envisioned as a candidate, but not a serious one, became much more prominent in the last few years, where STM, atomically resolved STM experiment, showed that actually, in most of the case, your density of states is maximal on the bonds in between two carbon atoms. And this is what you can see here. This is an STM image from the Grenoble group. Okay, so essentially all of these different states have different electrical and thermal properties. And the idea is that those two states, the interferomagnet and the calculate distortion, are supposed to be electrical insulator but thermal conductors, whereas those two states are supposed to be, well, this one is electrically conducting on the edges and thermally conducting on the edges, but not in the bulk. And this one is both a bulk edge insulator. And so what we wanted to do is to probe all the assumption, to probe this phase diagram using a heat flow measurement. And so to do that, that's where I can go a little bit faster because I've shown you already all of this. What you need to do is a sample that will essentially be a red brick at some temperature connected to a blue brick at some other temperature through a piece of graphene that we set at nu equals 0. And of course, now you know how you realize this red brick with a tunable temperature and this purple brick with a tunable temperature, and how you control and measure those temperatures. And essentially, each of those bricks, each of those reservoirs is a floating ohmic contact that is connected to the sample, which has this heat transport geometry. So essentially, you heat up that guy, and then you check whether the temperature of the other guy, the purple guy, increases or not. Okay? And so that's a typical cartoon of the sample that we realize. Again, a source, a detector, coupled one to another through a piece of graphene that we tune to nu equals 0. And we can heat up and essentially measure the temperature of each of those two reservoirs by those quantum Hall circuits, which is essentially another piece of the graphene flake that we tune independently to some finite Philip factors. All right, and this implements exactly what I was describing you at the beginning of the talk. And that's a typical micrograph of the image. And let me show you the typical results, and then I'd be done. Essentially, here I'm showing the increase in temperature of either the source in red and the detector in purple as a function of the heating current for the source. And this is exactly the same kind of data I was showing you before, right? You have this V-shaped curve for the temperature of the source. You see that the detector, the temperature of the detector increases by a little bit. This comes out of the noise, but it's actually quite small. And you see another thing, you see this black line here, and this black line would be the expected temperature for the source in the absolute transport here in nu equals. So this is already telling you that there's not much going on in this nu equals 0 region coupling the two, the source and the detector. And we can try to compare our results to the theoretical predictions that were done for bilayer graphene, but it's the same kind of physics, and the numbers are roughly in the same ballpark. And this dashed curve here would be the temperature of the detector that you would expect from the estimation of the heat flow at nu equals 0. And essentially what this tells you is that we are able to measure something of a small heat flow that is about 50 times smaller than what we would expect. Okay, for the sake of time, so we've done this experiment in various configurations, several samples. We've always seen that if there is heat flow at nu equals 0, it's very, very small. And let me, wrap up by essentially telling you what the conclusions, or at least the partial conclusions are, is the fact that, so every time we measure something that is both an electrical and a thermal insulator. And if you refer to the standard theory, there's only one candidate that is both electrically and thermally insulating. It's this fully sublattice polarized phase. But we know that this guy, we only obtain only when graphene is aligned with Bn, and we have very strong proof that in most of the sample it's not aligned. And so essentially what this, our conclusions is that in this complicated phase diagram of nu equals 0, where you have thermal conductions through essentially collective modes like spin wave or valley waves that should conduct energy, all of those modes should be at least gapped. And the reason for why they would be gapped is still to be investigated. It could be that you have different domains in your sample, which essentially gives rise to some diffusive heat conduction that's much lower than expected, some coexistence of these different phases, so something that's actually much more complicated than this already quite complex phase diagram, some more theoretically complicated symmetry breakings that I'm not a master of, or some other stuff. And yeah, so that was a typical, it might maybe have been a bit too fast. You let me know at the end of the talk. But that's a typical example of the kind of stuff we can do with heat transport. Again, we're not the only ones doing that. In particular, in this work on E=0, we published in back-to-back with our friends from India, from the group of Anindya Das in Bangalore. He did the same kind of experiment in barrier graphene with the same kind of result, that there is no heat at E=0. And now we are moving to more complex quantum Hall states, quantum that we have in a line graphene with HBN, more complex non-abelian phases of the fractional quantum Hall effect, and so on and so forth. And yeah, let's see where this takes us. And with this, I'm done. Thank you very much. If you have any questions, I'd be happy to take them.
Okay, so thank you very much, Francois, for the talk. Are there any questions, comments concerning the presentation?
So maybe one question from me to you. Was this understandable? How you guys got it? Okay, good. That's like number one thing. Then it's your question.
Okay, so according to...
Francois, sorry, just a question concerning the different phase
Yeah.
that you wrote on the spin. Can you comment again, you said about the antiferromagnetic situation, you exclude because the thermal...
Yeah. Basically, at least when we started investigating this physics, we were thinking, oh, look, it should be this antiferromagnetic phase, which means that it has a finite thermal conductance, and then we can try to induce a transition between this antiferromagnetic to ferromagnetic phase, and to try to see how the thermal conductance goes to zero. And what we saw is that, actually, we don't measure any thermal conductance. In between, there was this work, this STM work that showed that, where do I have it? It's before. Yeah, that shows that most likely for standards, up to some caveats, but most likely the good candidate would be the calculated distortion phase. It still brings quite a lot of questions. The idea, so this goes in a bit more detail now. People originally thought that it would be the antiferromagnetic phase. First, because the estimations of the parameters for the interactions gives you something that is in between those two guys with some preferences for the CAF phase. And then in this work, in this 2014 paper by the MIT group, they saw a transition between the CAF to the ferromagnetic phase. And the way this transition behaved, there was basically no closing of gaps or anything. They see it in transport, indicated that it should be something, basically they saw a transition from something that is insulating to something that is not insulating. And the way this transition behaved pointed to a transition between this and this. But then people realized that you can have this, you can have this, so it's, yeah, it's still, it seemed to be somewhat understood in 2018-ish, and now the STM experiment basically put everything back on the table.
Other question? I have one.
Yes.
Concerning the, can you hear me? No? So concerning the setup, at some point you say that with this setup we can measure also counter-propagating neutral mode in the fraction. The setup is only for counter-propagating, or you can access also case in which the neutral mode are co-propagating? It depends. The direction plays a role in that setup?
Yeah, so basically, let's use this standard stuff. So with this simple geometry, essentially if you have a neutral mode, whatever the direction of propagation, it's going to add a contribution to heat transport. And essentially, if it's co-propagating, which doesn't occur very often, except for some cases non-abelian, then you will just increase this number n by, let's say, 1, if it's perfectly coupled. Most of the time in the fractional quantum Hall effect, when you have those, you expect those neutral mode, it's in whole conjugate states, like 2/3, 8/3, this kind of stuff. And essentially, what you see is that you would, I mean, you, how to say it? You see that n is not completely quantized. And essentially, it tells you that you have a neutral mode that is counterpropagating and that is equilibrating, that is exchanging heat with the let's say, the forward-going modes. And so there is one way that Moti Heiblum did and that we could sort of implement in our geometry to see whether a neutral mode is basically flowing downwards or, I mean, downstream or upstream, is essentially to have this kind of experiment where here you set this guy to the fractional quantum Hall state that will host neutral mode, and let's say here you put some kind of ground. So you make a difference between one edge and the other, and by doing that you can see, for instance, if the normal transport carries heat, let's say from here to here along this edge, and you put a ground there, then you will not see any heating. But if you have counter-propagating neutral mode, you will see that the detector heats up. So that's the general idea. All right, thank you guys. I'm here for the whole day, so if you want to discuss, I'm available. Yeah, don't hesitate. I'd be happy to, and you know. All right, thanks.
Sorry, I missed the last 10 minutes.
It's good. It was a little bit rushed through because.